Hello, this is video 4.3 on kinematics and dynamics. In this video we will look at how rigid bodies behave under the influence of forces and torques that are being applied to them. And then we will see how we can use that to model the motion of a quadrotor depending on the thrust of its motors. So kinematics in general describes the motion of rigid bodies. Typically you can describe the state of a rigid body then in classical mechanics by its position in space, by its current velocity and by its acceleration. And then you can find very simple rules. Know that if you integrate up acceleration you get the velocity, if you integrate velocity you get position. And just to immediately give here an example how this might look like. Imagine that we are looking at a rigid body that is floating or that's living in a one-dimensional world. So we can describe its position just by using a scalar x, describing its position in this space. You can describe its speed also by a single scalar x dot, and then its current acceleration by x double dot. And then we can apply an action to it that in our example now just is being added to the acceleration of this object, and we need a time constant delta t that tells us how much time passes by from one moment to the next. And then given that we can derive or we can specify a linear process model that tells us how we can evolve our state from time step t minus 1 to time step t. And you've probably seen that before. You can say that the current position equals the previous position plus delta t times our current speed. This is the first row of this system matrix. In the second row we have the relationship that the current speed depends on the previous speed plus delta t times our current acceleration. We just keep the acceleration the same as long as nothing else happens. And then to this state we add our control input u just by this simple vector 0, 0, 1, which just means that we add the action to our acceleration. And using that you can already get a simple dynamical system of an object that floats in one-dimensional space. Now dynamics is the theory that relates forces and torques to such accelerations. As you might know from school, forces induce a linear acceleration on the body, while torques induce an angular acceleration. You can say a torque is the turning force that makes something turn. But let's start with forces first. You can consider, or a force can be represented by a vector, and they can be summed up. So if you, for example, apply two forces to this soccer ball here in x and y direction, then this corresponds exactly to the force if you would have applied a force along this diagonal line fx plus fy. And the force that you apply to an object directly relates to the acceleration that this object perceives. So, and this acceleration then also depends on the mass of the object. So a heavier object is more difficult, of course, to be accelerated or to be moved. A torque is you could say, loosely speaking, is the turning force. So if you have a lever arm that you try to move, you can apply a force on one side, and that will induce then a torque on the rotation axis. And this torque that is generated depends on two things. It depends on the force, of course. The more force you apply to the lever arm, the more torque you get, and it depends on the distance of the place where you apply the force and the rotation center, which is denoted here in this graphics by r. And as before, it also depends on the mass or the mass distribution on the object, and that is typically captured by this inertial matrix J here that then relates the torque to the angular acceleration, here denoted by bold alpha. Good, and now let's see how this translates to quadrotors. As you've seen before, the quadrotor consists of 4 propellers, and every propeller generates some thrust, and this induces a certain force. So we have now 4 sources of force that push the quadrotor up, and we have the gravitational force that pulls the quadrotor down at the same time. If we count all of these forces together in the vertical case, then the quadrotor hovers exactly in place if the thrust forces of all 4 rotors exactly match the gravitational force that pulls it back down again. And at the same time, every propeller also induces a torque, which is the counter torque that's generated by moving the air, or by the propeller moving the air. And we have to make sure that all of these torques actually sum to 0 in order not to get any motion. So this graphic shows again, now if we want to hover in place, all of the 4 forces have to equal the gravitational force. If it's larger, then we actually accelerate to the top. So the resulting force is the force that's being applied then to the rigid body of the body of the quadrotor. Now, if we turn the quadrotor slightly, then this thrust force is not in line anymore with the gravitation, and this means that only part of this goes in. We can separate this resulting force from the rotor thrust into a vertical component Fz that compensates then for the gravity, or that has to compensate for the gravity if we want to keep the same position, and an x and y component that actually makes the robot, the quadrotor, go forward or sideways. And because all of these vectors or forces are actually vectors, we have to transform the thrust vector into the global coordinate system by using, for example, a rotation matrix, to be able to compute the acceleration in global coordinates. Then, if we want to change the attitude of our quadrotor, we can bring the motors into a mode where the 2 opposite motors produce unequal thrust, and this then induces a certain torque around the rotation axis, or the center of mass of the quadrotor. Again, by the formula from a few slides before, we can then compute the resulting torque, and that leads, given this inertial matrix J, to a certain induced angular acceleration alpha. Good. And then for rotating around the vertical axis, we can also modulate the speeds of the rotors in such a way that the sum of the torques does not equal 0 anymore, but that the left-turning motors are turning faster than the right-turning ones, for example, and that induces then a torque on the overall system. Good, so this already summarizes this video. We've looked at rigid body kinematics. Just remember that every rigid body can be described using its position, velocity, and acceleration. Then we looked at how forces and torques what accelerations forces and torques actually produce. And then we just applied that to quadrotors because this is what we need.